Okay, in this video I want to discuss the x-intercepts of a parabola, if they exist. Okay, sometimes they actually don't, but we'll talk about that in greater depth later. The x-intercepts of a graph are the coordinates of the points, or the x-coordinates of the points, I should say. Let me throw that in there. The x-coordinates of the points, if any, where the graph crosses the x-axis, okay? Just for you to know here, sometimes people say the x-intercept is the point itself, okay? So sometimes people would say it's the point itself. Other people would say it's just the x-coordinate of the point. I'll just let you know what I'm doing in each case here, okay? Okay, so with that definition in mind, if the equation of the graph is y equals f of x, then because every point on the x-axis has y-coordinate equal to 0, right? Okay, to find the x-intercepts of the graph, we need to solve this equation. So you're just going to have what? Y set to 0. So you've got f of x equals 0, and you need to solve that. The solutions would be what? The x-intercepts, okay? All right. In the case of a general parabola, okay, we're talking about parabolas now here, we know our function looks like this, right? ax squared plus bx plus c. So that's going to be set to 0. Just a reminder, a is not 0 to be a parabola, okay? And we need to solve that thing for any real solutions, okay? Real solutions. We're going to see problems of this type sometimes do not have any real solutions, okay? They will always have what we call complex solutions, but more on that in a future video, okay? Now, looking at this equation here, we might recognize this as solving a quadratic equation. In fact, this is what we would call a quadratic equation in standard form, where I've got what? The quadratic polynomial written in descending order and 0 on the other side of the equation, okay? So a quadratic set to 0. That would be what we would call standard form. So this is actually in standard form, okay? Now we're going to talk about methods of solutions here. There are 3 basic methods of solutions. Okay, I guess I could say there's 4 methods. If you actually have the parabola graphed like on Desmos, you can actually see where the x-intercepts are graphically, right? Okay, so that's so easy there that I'm not going to even cover that. But let's talk about the algebraic techniques, assuming that we don't have the actual graph of the parabola. Okay, so there's 3 basic techniques of solution. Okay, factoring. Okay, sometimes that works. Sometimes it can't really be done easily. Okay, completing the square. Okay, I'll show you how that works. And then the last method is the quadratic formula. Now, method 3 is based upon method 2, completing the square. This is so important that I'm in fact going to devote an entire separate video to that. Okay, so the next video will be the quadratic formula. Okay, but I'm going to show you examples of number 1 and number 2 in this video right here. Now, I must say that the quadratic formula will always work to find the solutions to quadratic equations like this, ax squared plus bx plus c equals 0. Okay? Okay, the quadratic formula always works. But we got to build our way up to it here. And it's not always the easiest mode of solution here. So the first thing I always like to do is, oh, wait, I do mention this. Oh, by the way, the quadratic formula is actually obtained by completing the square in general, okay? So we're going to complete the square on that general ax squared plus bx plus c equals 0, and that will generate the quadratic formula for us, okay? But again, that's going to be a separate video. Okay, let's talk about solution by factoring. This is the first method I usually try if I'm trying to solve a quadratic equation, okay? So let's take this problem here. Find the x-intercepts of the parabola y equals f of x equals x squared minus 3x plus 2. Okay, so you guys see here what we want to do to find the x-intercepts you've got to take that quadratic, x squared minus 3x plus 2, and set it to 0, and we get this quadratic equation here, okay? Now, I'm not going to review in depth or anything here the factoring, okay? So that's something you can look up and review yourself here for college algebra, but I'm just going to go over it here. If you were to actually factor this thing, by the way, this is a monic quadratic. What does monic mean? What does mono mean? Mono means 1, right? And monic means 1 in the leading coefficient. Okay, so the coefficient on x, assuming you've written it in descending order, the leading coefficient is 1. That makes it a monic. Monic quadratics are easier to factor. This is monic, so it's really not very hard to factor here. Okay, because the first two terms, if it factors in the integers here, would be what? X and x, okay? And then you just have to worry about finding the constant terms on each of the factors. Now, in the case of a monic factorization like this, you're looking for what? Two factors whose product is the plus 2, but whose sum is negative 3. Now, you play around a little bit, and I think you can come up with the integer solutions negative 1 and negative 2 here to fill in those places here. Okay, so we actually have this factorization. X minus 1 times x minus 2 is equal to 0. Now I skipped writing out this step, but I'm sure you're familiar with it. Since the product of these two factors is 0, by what we call the zero product principle, that is, if a product is 0, the only way that's possible is if at least one of the factors is 0. Okay, so to find all the solutions of this equation, what we do is take the first factor, x minus 1, and set that equal to 0, and then solve it. Okay, now when you show work on solving this, as far as I'm concerned, you can jump right to the solution like I did. Okay, you can see x minus 1 equals 0 has solution x equals 1. Likewise, x minus 2 is equal to 0 has solution x equals 2. So these are our solutions here, okay, to that equation. So we would make this statement. The x-intercepts are 1 and 2, okay? And like I said here, some people will actually write those x-intercepts as points instead. Now, because these are points on the x-axis, the y-coordinate is 0, as we stated originally. So we could say the x-intercepts, in other people's parlance here, other people's language, 1, 0 or 2, 0. Okay? Or I should say, oops, not and. That should be and, since I'm just listing the intercepts. Okay? 1, 0 and 2, 0 are the x-intercepts. Okay? Their solution by factoring. Okay, let's take a little bit harder factoring problem here. Okay? Again, you can play around with this where I'm going to go 2x squared minus x minus 3 is 0. That would be my corresponding quadratic equation, solving for the x-intercepts, okay? Okay, now you can play around here. You notice that this one is not monic. The leading coefficient is not 2. This makes it just a little bit harder here. But 2 doesn't factor in too many ways in the integers. 1 and 2, or negative 1 and negative 2, but there's no point in using negatives on both of these. You could factor both those negatives out and they would cancel. So I'll just go 2x and x, okay? Then you're going to have to look for what? Two factors whose product is negative 3. And when foiling this out, gives you the appropriate middle coefficient of negative 1, okay? Well, I worked this out a little bit here. Again, you can review factoring if you need to. But it factors as 2x minus 3 times x plus 1. Alrighty? And take each factor, set it to 0, and solve. So you get x equals 3 halves. You get x equals negative 1. So the x-intercepts are negative 1 and 3 halves. Or, if you prefer, as points, negative 1, 0, and 3 halves, 0. Okay? Usually I like to box in my answers and have you guys do the same. Okay? Usually I'm not writing with a mouse though, but there it is. Okay, boxing in my final answer. Now let's talk about a more powerful technique here. Okay, solutions by completing the square. Let's find the x-intercepts of this parabola. Y equals h of x is x squared minus 2x plus 5. Now you know I have to take the x squared minus 2x plus 5 and set it to 0. Okay, now I need to solve that. Now I'm going to use this completing the square idea. Now it's going to be in a slightly different form than what we did in finding the vertex of a parabola using completing the square, but it's actually in some ways a little bit simpler. Okay, let's go ahead and do this. Here's the first thing you want to do. You want to isolate the two x terms, or whatever the variable is. You want to isolate the two x terms and get the constant term on the other side. So the first step I'm going to take is to add 5 on both sides of this equation. Okay, so add 5 on both sides. And then I've isolated on one side of the equation the x terms. Okay, so I've got this x squared terms and I've got the minus 2x. 5 is over on the other side. Okay, so you can see where I've written that here. X terms only on one side. Okay, so that's your first step. Your second step here would be to divide on both sides by the leading coefficient. Okay, but you guys notice that once again this is monic, right? This is monic because the leading coefficient is implicitly 1. If I was to force a leading coefficient there on the x squared term, it'd have to be 1. Okay, I would divide on both sides by 1, but there's no point in doing that. Dividing by 1 doesn't change anything. So I'm basically skipping that step. And now I'm completing the square like we usually did. Now this is a monic, a quadratic here. So you remember the trick? I've got to add a certain number to get a perfect square. What do you do in this monic case? You take half the coefficient on x, which is negative 2, okay, and then square that. So I go negative 2 divided by 2, and then I square that result, I get 1. Now when I take that 1, that magic number, and add it to these other two x terms, okay, and add that 1 there. Now if I add it on one side of the equation, I have to add it on the other side of the equation also. Lots of people make errors. They, for some reason, forget to add on both sides of the equation to keep it balanced, okay? So don't forget what you do on one side of the equation, you have to do on the other, okay? I'm just saying statistically, I've noticed there's a lot of, when people make errors, that is a common error. So when you get that 1 there, that magic number, add that 1 to both, or whatever the number is, add it to both sides of the equation. And what should have happened if you did this correctly is this thing now should be a perfect square. Okay? So that's a perfect square. And in fact, if you think about it just a little bit, that's the square of x minus 1. On the other side, we get what? 6. So we've got a new quadratic equation here. But this is easy to solve by taking square roots. Now, here I'm going to take the square root of both sides of that equation. Okay? The square root of x minus 1 squared is in fact not x minus 1, it's the absolute value of x minus 1. Do you remember this? You got to be careful here. If I'm going to take the square root of z squared, that is not z in general, it's the absolute value of z. Okay? For example, if I had the square root of negative 3 squared, okay, that would be the square root of 9. The square root of 9 is 3 and only 3. Notice that how I got a change in sign here? It went from negative 3 to positive 3. Okay? It's always the absolute value of whatever the z is. Okay? In this case, my z is x minus 1. So I've got the absolute value of x minus 1 is the square root of 6. Excuse me. Okay? Now this has two solutions. Okay? There's actually two different numbers whose absolute value is the square root of 6 plus the square root of 6, or the square root of 6. Negative square root of 6 also has that same absolute value. So this actually reduces to this once I get rid of the absolute values. So x minus 1 is plus or minus the square root of 6. Adding 1 on each side to isolate the x, I get x equals 1 plus the square root of 6. And you could calculate that on your calculator to get a certain decimal place accuracy if you wished. As far as I'm concerned, that's fine the way it is. Okay? Alrighty? Now, when we're working these problems here, okay, I want to throw this in now. You're free You don't have to write, you see this work here? That's very persnickety, very careful logic. That's fine, that's good. But if you want to, you can jump from here down to here and still get full credit with me. Okay, so these, you can hide these in-between steps. Officially, they would be there, but you see what if you see what you're doing here, you see that the x minus 1 has to be plus or minus the square root of 6 almost automatically here. So jump from here to here, that's fine. So you don't have to write these in-between steps every time. Okay, but it's important for you to see this and to understand this principle over here that I mentioned here. Okay, alrighty? So I will be skipping that step later on here, but understand the logic behind it. Anyways, okay, let's do another one. Let's keep going. Okay, let's do another one. Now notice here, I didn't even couch this in terms of x-intercepts or anything like that. I'm just jumping in here, okay? You know, like in this problem, the x-intercepts are these guys. I didn't write them as points. This time I'm just jumping straight to a quadratic equation, okay? And that's what I'm going to be doing in the next video, okay? But let's do this. We want to use completing the square on this, okay? Now, do you remember what the first step? Take the constant term here. I want the constant on the other side. So implicitly, I haven't written it. I'm adding 5 on both sides here, okay? So I've isolated the x terms on one side and the constant term on the other side, okay? All right, looks good, okay? Now let me point out this time, that's not monic, okay? The leading coefficient is 2, it's not 1, right? So what I want to do is divide by 2 on both sides of the equation, okay? You're seeing how this is a little different than the completing the square technique we used before, okay, rewriting a parabola. It's actually a little easier in my opinion, but I divide on both sides by 2. Now what that is going to do is have the effect of what? That 2 is dividing both terms, right, in the quadratic. So I'm going to get 2 over 2 x squared. 2 over 2 x squared is really what? 1x squared or x squared, right? That makes it monic. Notice here I've got what? 1/2 x, and over here on the other side I've got 5/2. So I've got to divide by the leading coefficient on both sides of this equation to make this into a monic quadratic in order to use my little trick, okay? Remember my little trick was finding just the right number to add to both sides of the equation to make the left-hand side here a perfect square. Now you remember how that worked? Okay, I take the coefficient on x, which is 1/2, divide it by 2, okay? All right, so that ends up being a quarter. Don't forget to square here, okay? So I actually got 1/16, okay? 1/16. Again, add 1/16 on both sides of the equation, okay? Now, what's the magic thing? What should be happening here? The left-hand side of that equation should now be a perfect square, okay? And in fact, it is. I claim it's the square of x plus 1/4, okay? X plus 1/4 squared, okay? If you were to FOIL this out, okay, I would get x squared, right? I would get 2 times the product of these two, so that would be 2 times 1/4 times x, which is 2/4 x, which is really 1/2 x. Cool. Plus 1/4 squared is a 16th, so there it worked. Now I have to add these two fractions here. The common denominator is 16, so that's actually 41 over 16 when you perform the arithmetic here. Okay, now here I'm going to just jump to it. I take the square roots of both sides to get rid of absolute values, yada yada. X plus 1/4 is plus or minus the square root of 41/16. Now the square root of 41, that's an irrational number, but the square root of 16 I can just write as 4. So I made that a little bit nicer denominator there. The numerator is just plain ugly, okay? 41 is in fact a prime number. We can't even simplify the square root there. Okay, now I need to isolate the x. So I'm going to do what? This is what's typically done here. I'll add a negative 1/4 on each side, okay? Rather than thinking of it as subtracting 1/4, add negative 1/4 on each side. X is negative 1/4 plus or minus the square root of 41 over 4. You notice that these two have a common denominator, so I can write that more compactly as x equals -1 plus minus the square root of 41 over 4, and those are my two solutions here. Okay, alrighty. It is just a tradition to have what? The rational part, and then what? Plus or minus the square root part. That's why up here I'm actually adding a -1/4 on each side. Okay, so the what they call the quadratic surd part comes second. Okay, it's just our tradition here. It could have been different, but that's the way things worked out. Okay, all right. Well, I hope you understood this stuff, because I'm going to give you some questions along these lines. All right.